Okay, year 12 further, so here we go with the impulse and momentum assessment. I've got to say this is a really nice one, so hopefully you've enjoyed it as much as I have. So starting off with just drawing a diagram here. So you've got here you go, so A mass 1200 kilograms traveling at 15 meters per second, there it goes. B is mass 800 traveling at 10 in the same direction, so A is catching up with B, they're not colliding head on, it would have said. Afterwards we'll expect this to be the situation. Alright, looking at that, A is heavier than B, so bashing into B is probably not going to turn it around, so we can assume VA going that way. If it did, then we just get VA as being negative in our calculations. Okay, so that's all of that. On to B here. So now notice that we are given some information regarding our Newton's restitution. And we know that our E is equal to our separation speed over our approach speed. And so in this case we've got that 0.8 is going to be equal to VB minus VA, so that's our separation speed. The approach speed is 15 minus 10. Okay, so we can simplify that, so that's obviously 5 times 0.8 is 4, so 4 is equal to VB minus VA. I'm going to leave that hanging because I want to do something more with it in a minute. So that is all from our E, our Newton's law of restitution. We can also look at our conservation of momentum in that situation here. So there we've got 15 from the first one times by 1200 plus 800 times 10. That's all of the momentum beforehand. Afterwards our momentum is 1200 VA plus 800 VB. Okay, so that is 26,000, and that is still that. We can just divide through here, and this will simplify it down. We can divide through by 400 because that's the highest common factor of all of this, giving us 65 is equal to 3 VA plus 2 VB. Okay, right, it's just a little bit quicker to, I'm going to call that equation 1, I'm going to call that equation 2. It's just a little bit quicker to actually use the old simultaneous equations methods here. Like you could just put these into your calculators and get the answer. So in fact I think that's what we will do. So but if you were to do that, you'd end up getting that VB is equal to 15.4 and VA is equal to 11.4. So there we go. Two simultaneous equations, pop into your calculator, those will be your answers. Alright, moving on to 3. So what happens now is that they will bash into each other. Let's draw it first. And so there's car B, that was weighing 800 kilos, and that's moving along at 15.4 meters per second. And car C is stuck there doing not very much at all. That weighs 740 kilograms. Okay, afterwards they will become entangled. So B and C, just call it BC there, is going to weigh at that point, it's going to have mass of 1540 kilograms. It's going to move on at some unspecified speed, which we're going to call VBC. Okay, so now we just need to look at our conservation of momentum. And so beforehand our momentum is just 800 times by 15.4, and afterwards our momentum is going to be 1540 times by VBC. Okay, so just dividing by that will give us that our VBC is equal to 8 meters per second. Okay, so that's all well and good. On to part 4. For this one, let's have a little look at what's happening in the situation before now. Okay, so there's another collision. So A, which we left a little while ago, but it's still been trundling along, so it still weighs 1200 kilos. It's still called A, and it's still moving at 11.4 meters per second. We got that from our simultaneous equations earlier. And B and C then went off and collided with each other, and now BC, as we'll call it, is moving at 8 meters per second. So of course what's going to happen is that A is going to then catch up with this entangled car BC. Okay, so it's going to bash into it, but we don't have to do too much about this because we've now got the speed they separate at is 2.55 meters per second. So all we've got to do is work out E. So E, as we know, is going to be our separation speed over our approach speed, and we know that our separation speed is 2.55 because we're given that. Now our approach speed must be 3.4 because that's just the 11.4 take away the 8. Punching that into our calculator gives us very nicely that E is 3/4. Alright, so that's question 1 all done, which is very nice. Question 2. So very nice with Jeoffry the cat jumping onto a sledge. How fun. I'm sure there must be lots of little videos of animals doing similar stuff. So here's Jeoffry, and Jeoffry weighs 4 kilos, which is quite heavy for a cat. And he's going to jump onto the cat. He's going to be moving at 2.25 meters per second. So I mean, if you were a mouse, that would be utterly terrifying, wouldn't it? This massive cat moving at that kind of speed. But anyway, he's not out hunting, he's going for a play on the sledge. There we go. And then obviously Jeoffry and the sledge are together, so we'll call that JS, and that now weighs 12 kilos, and that is moving at some unknown speed, so we'll just call that V. Okay, and all we're going to need to do to find this, or to show this indeed, is just use our conservation of momentum. So before, the momentum is just 4 times 2.25, and afterwards the momentum is 12V. And so all we've got to then just do, so V is obviously going to be 4 times 2.25 is 9, so 9 divided by 12, which is of course 0.75 meters per second. Okay, good. Alright, moving on to question 2. So now what's going to happen is that Jeoffry and the sledge are moving on. They're going to hit a stone. Oh no, the stone weighs 3 kilos and it can move around on the ice, so it's not restricted in any other way. And we've got a restitution given to us, which is all well and good, and we've got to find out what happens to the sledge and Jeoffry after the collision. We'll probably work out what happens to the stone as well, because we'll get simultaneous equations and they'll get our answers for free, so why not? So here we go. So here's JS, Jeoffry and the sledge, and they are 12 kilos now, and they are moving at 0.75 meters per second, and they're going to hit the stone. I just have to call it stone because we already used S for sledge, and that stone weighs 3 kilos. And what's going to happen afterwards? Well, they're quite heavy, so probably they'll keep moving in the same direction. So 12 kilograms JS, we may as well call that V1, and because I don't want to use too many subscripts, I can help it. And 3 kilograms with the stone, so that's going to get bumped on, and that's moving up there, stone here. Okay. Alright, so we've got 2 things to look at here, because obviously it's a lot of marks. So first off, we're going to have to look at conservation of momentum. So before, our momentum is just 12 times 0.75, and afterwards our momentum must be 12v1 plus 3v2. Okay, well that will simplify down quite nicely to give us our first simultaneous equation, which is 3 is going to be equal to 4v1 plus v2. We can also, if we look at Newton's law of restitution, we can also get that from our E, which is our separation speed over our approach speed, and so that means that we've got 4/15, and that's equal to V2 minus V1. That's going to be our separation speed. Our approach speed must be 0.75 because the stone was stationary beforehand. So that will then give us, if we just multiply that up there, that ends up giving us that 1/5 is equal to V2 minus V1. So we've now got our 2 simultaneous equations here, call them 1 and 2. So we can just punch those into our calculators, and we will get that V1 is equal to 0.56 and V2 is equal to 0.76. There we go. Alright, moving on to part 3. This is a wordy one. The centre of mass remains in the same position since there is no external force present in the horizontal direction. Okay, so centre of mass remains the same. One mark, no external force present horizontally. Second mark. Alright, okay. Question 4. Okay, so what's happening now? So we've got a little bit of relative motion coming in. Now, relative motion was a big deal back on the old A level. I used to love it. There's a little bit of it kind of in this topic, but not very much. So we do kind of need to be sort of aware of what's going on. So I've got, there they are, Jeoffry on the sledge, weighing 12 kilograms, not doing very much. Okay, afterwards what's happening is that Jeoffry is getting off the sledge. So Jeoffry is going to move off that way, and of course the sledge must go in the opposite direction. Jeoffry weighs 4 kilos, the sledge weighs 8 kilos, and we want to find out the speed the sledge is travelling at. We're going to call that Vs. Now it says that Jeoffry has left the sledge, his horizontal speed relative to the sledge is 3 meters, not just like relative to the still earth or something, but relative to the actual sledge. So this means that Jeoffry will be travelling 3 meters relative to the sledge. So that means that the velocity of the sledge minus the velocity of Jeoffry, that must be equal to 3. And so the velocity of Jeoffry is going to be the velocity of the sledge minus 3. Okay, so that means at this point we're going to call this Vs minus 3. Okay, so we can now go, right, so momentum before was 0, and momentum after is going to be Vs minus 3 times 4 plus 8 lots of Vs, and so that gives us 0 is going to be equal to 4 Vs, that's an S, minus 12 plus 8 Vs, and so we've then got, that's said 12 and I wrote 4. So I've now got 12 is equal to 12 Vs, and so 1 is equal to Vs, meters per second. Okay, cool, there we go. Alright, so now on to question 3, which we're going on from cute cats to science fiction spaceships and all of that stuff, so that's all very nice and well and good. Okay, so we got here that here's our situation. We've got A 100 kilograms, B 200 kilograms. They're moving this way, alright, but what they want to do is bring the two spaceships together. There's a wire between them, so by some kind of mechanism there's a tension in the wire, and that puts an impulse of 100 newton seconds, acts on both of these spacecraft. So we've got to show the new velocity of A is 31 meters per second in the original direction of motion, and find the new velocity of B. Okay, where's my little thing on page? Right, there we go. Okay, so we know that our impulse, that is the change in momentum, okay? Change in momentum. Sounds like Mr. Marshall's lefty writing there. Not there's anything wrong with that. Okay, so impulse is 1100. So for this one, the change in momentum is going to be the final momentum subtract away the initial momentum. So the final momentum is going to be 100 V, and the initial momentum will be 100 times 20. And so we've got 3100 is equal to 100 V, and so 31 is equal to V, which is what we were asked to show. Right, if we're looking at the other one's going to slow down, so its impulse is going to be negative, so it's going to act in the opposite direction. And so you've got minus 1100 is going to be equal to 200 V minus 200 times 20. So we're just considering moving to the right as positive. So if we can now, obviously that's 4000, so 2900 is equal to 200 V, and so 14.5 is equal to V. Okay, so that's all well and good, so that's that one done. Moving this on. Okay, Alright, so the spacecraft collide with a direct impact. The coefficient of restitution is 3/4. Show that the velocity of A after the collision is 11.75 and the original direction of motion. Right, so we need to just draw this out. So to do that, so we got here that A, that weighs 100 kilos, and that's going to be coming this way at a speed of 31, and B, a bit bigger, that weighs 200 kilos, and that's going to be going this way with a speed of 14.5. Now afterwards they'll bump into each other, but we're expecting that A, only being 100 kilos, is just going to be on a bit more, and so that B's speed will bump up to VB, whatever it is, and VA will stay, A will stay at VA, and they'll still have the same masses. Okay, so we can look at the conservation of momentum in this situation. So for this one we've got 31 times 100 plus 14.5 times by 200, and that's going to be equal to our momentum afterwards, which will be 100 VA plus 200 VB, and that will all simplify down to a nice simultaneous equation of 60 is equal to VA plus VB. Call that equation 1. We can also look at Newton's law of restitution, NLR, and we know that our E is equal to our separation speed over our approach speed. That's going to give us, we told E is 3/4. Our separation speed is got to be VB minus VA, and our approach speed is going to be 31 minus 14.5. This will simplify to give us 12.375. It's going to be equal to VB minus VA. Call that equation 2. So we've got two simultaneous equations now. So if we slam those into our calculators, we will get that VA is equal to 11.75 meters per second, and VB is equal to 24.125 meters per second. Okay, so there we go, there's our two answers there. Alright, part 3. So now, before the wire comes taut again, a component of spacecraft A is fired off in the opposite direction of motion. The component has mass 20 kilograms, the main part of A, and the component is separated 70 meters per second. So show that the new velocity is this, and it's in the opposite direction of motion. So what have we got going on here? So we've got, to start off with beforehand, we've got 100 kilos, and that's moving at 11.75 meters per second that way. Afterwards, you've got a component which is going travelling that way, and that weighs 20 kilograms. We'll call that C. That's going to be travelling at what we just have to call VC. And then we've got A. A is now a little bit lighter. A is travelling at VA, and it weighs 80 kilograms. Okay, so we can look at the conservation of momentum, and we can see for sure that that VA, so beforehand we've got 100 times 11.75, and that is going to be equal to 80 VA minus 20 VC, and this would simplify down to 235 is equal to 16 VA minus 4 VC. Okay, so they divide through nicely by 5. Alright, now they call that equation 1. Okay, now we're also told that they separate at 70 meters per second, so that therefore must mean that 70 must be VA plus VC. So just adding the speeds together will be 70. That's what that means, they separate at 70. So we've now got our two equations, so we can just pump those into our calculator, and we're going to get the VA is equal to 25.75 meters per second, and VB is going to be equal to VC, sorry, is going to be equal to 44.25 meters per second, which is what we were asked to show. Okay. Alright, and the final bit is to calculate so the two spacecraft will now collide and coalesce. So A has now lost the component, so A is now moving and is going to catch up with B now. So A now only weighs 80 kilograms and it's moving at 25.75 that we just worked out. We weren't asked to work it out, but it's a good job we did because we need it now. And it's going to catch up with B now eventually, but it's a space, you know, so different kind of reality up there. So B weighs 200 kilograms. It's moving at 24, beg your pardon, 0.125 meters per second. So not much difference in the speed, but it will bump eventually. When it does, AB is going to move off at some unknown speed, which we'll call V, and that we'll call it AB, and it's going to weigh 280 kilograms. So we can just use conservation of momentum for this, and so we've got there 80 times 25.75 plus 200 times 24.125, that's going to be equal to 280 V. So just working that out and dividing by 280 gives us V is equal to 24.6 meters per second. And that is that, and I thought it was a lovely test, so I say well done to Integral for writing that. Nice little stories and good maths. So there we go. Hope you did well.